All right, can you hear me? Great. Okay, so this is joint work with a lot of people, some of them here, with Gorian, Anne, Bill, Tommaso, and Michael, and actually Anne is here, and Bill has also given a talk yesterday. It's probably here somewhere. My name is Christian Schaffner. I'm at the University of Amsterdam and at CWI and QSoft. And this talk, as you just looked up, is about encryption. So in a setting of encryption, we have our two heroes, Alice and Bob. Alice would like to send this plaintext message M to Bob over this channel. Unfortunately, this channel is overheard by the evil eavesdropper, Eve. So we kind of, and we assume in this setting actually that Alice and Bob already share a secret key. So they may maybe have run QKD and they have some nicely established secret key, a classical string that Eve doesn't know. So what we need to do is we want to come up with an encryption scheme, so a way to encrypt the message M to obtain a ciphertext running this encryption together with the secret key. And it should also come with a method of decryption, so where Bob can run the decryption of the ciphertext and hopefully recover the original message M. So if I ask in this room, how would you do that? I would probably hear, what do I hear? QKD, yeah, it's already been done. The key is there, so you just need to encrypt. How do you encrypt? One-time pad, exactly. You just do one-time pad. There's a classical version, which basically means you just do bitwise XOR of the message with the bits of the secret key, and the decryption operation is the same. Or there's also a quantum version of it that we've already seen called the quantum one-time pad, which basically, if you assume the message is just a single qubit, say, then you need two classical bits A and B to encrypt those, and basically these classical bits A and B that tell you whether you should apply a Pauli operation or not. And the decryption operation is also going to be exactly the same. And we all know that these two schemes are secure, and that's the end of my talk. Thank you very much. Now we can all go for lunch. Oh, not quite. Sorry. You have to wait a little bit more. So what do I really mean by this? What do we mean if you say that this thing is secure? And what we really mean is something like the following, namely we're talking about perfect or information-theoretic security. And this can be formalized as follows, namely let's say in the classical case, that the ciphertext distribution, what we get if we do this kind of operation, is statistically independent of the message distribution. So in fact, the message and the ciphertext have nothing to do with each other. They have information theoretically not related to each other. And similarly, you can argue in the quantum case. However, this kind of type of security comes at a very steep price. And there's this famous theorem by Shannon in a classical case that has been actually, there's some variations of it by Evgeny Dodis, and also you can prove something similar in the quantum case. Namely that if you want this kind of security, then the secret key has to be as large as the message. That's really unfortunate, and it's also very impractical. Imagine you want to encrypt all the video recording that has been made here over the week. Eventually it's going to be sent to YouTube somehow, and maybe you want to use an encrypted channel. And so all this gigabyte of data, if you want to encrypt it with this type of security, you're going to need gigabytes of keys. And keys are very precious material. Now, those are the things that are difficult to keep secret. So it's just not very practical and not really used in practice often. So what people usually do in cryptography is they kind of settle for something weaker, and they call this computational security. And then things get a bit more difficult to actually even define. And so if you want to define computational security, there's two things you can specify. And on the one hand, there's a threat model. So you'd say what exactly the adversary here can do. And on the other hand, it's the type of security that you want to achieve that you have to specify. And so on this side, one can kind of look at increasing capabilities of the adversary. We could assume that Eve is simply an eavesdropper, so basically just sees ciphertext flying by. But maybe a little more realistically, Eve maybe already knows what will be encrypted. So if she sees the ciphertext, she already knows an according plaintext. So that's like a more powerful attacker. Or even more powerful, she might be able to kind of even adaptively ask for plaintext to be encrypted. So using the same key, she could just ask Alice, well, what is the encryption of this particular message, and see the ciphertext. And it should still be secure so that if you see an encryption of a new message under the same key, you should know what it is. And even more powerful would be an Eve that can even ask for decryption of ciphertexts. So even if you're allowed to ask some decryption, you still should not be able to know what a ciphertext is without explicitly calling this decryption oracle. So these are things that people actually do study in classical cryptography. And on the other hand, you might wonder, like, what kind of security do we want to guarantee? So clearly what we want is, to start with, that the ciphertext, it shouldn't reveal anything about the secret key. Now, if it was the case that from the ciphertext you could just derive the secret key, well then the eavesdropper could just do the same thing as Bob and simply decrypt. So clearly that's not going to be secure. But also, you want to make sure that the ciphertext does not reveal the whole message, obviously. But now, getting a little bit tricky, maybe you want even more than that. Now you want to make sure that the ciphertext, for instance, does not reveal any particular bit or any particular part of the message as well. And if you think about this a little more, then you come up that, well, somehow you want that the ciphertext should not reveal anything about the message. Not any function of the message. So, but how do we formally do this? Unfortunately, classical cryptographers have already done this back in the days, quite a while ago. And they came up with this notion of semantic security. So this is a standard notion in classical cryptography. So standard that is, you can find it in textbooks like this one by Jonathan Katz and Yehuda Lindell. And it looks something like that. So this is quite a mouthful. But nevertheless, I would like to kind of guide you through this. And I made some pictures for that. So let me explain you the notion of semantic security that people usually use. So first of all, you start with a way of generating a message. Say there's some message generation algorithm that produces a message. And based on this message, you create two kind of substrates. One, there's some auxiliary information that's basically just applying some function h to m. And there's a target that you create by applying a function f to the message m. Now what you do is you take your message, you encrypt it with your encryption scheme. So remember, the goal is to define the security of this encryption scheme. So you take this message, you encrypt it, you give this to the adversary, together with the auxiliary information that somehow you might learn on the side. And then you ask the adversary to come up with this target here. So you ask, and all this together we call the real world. So in the real world, you ask the adversary to look at the encryption of M and this auxiliary information and see how well he can come up with this target here. So this is what you do in the real world. Now there has to be an ideal world. In the ideal world, it works as follows. There is a simulator here that does not get to see the message itself. It only gets to see the length of the message. So somehow, this is not what you're going to hide, because we assume like this encryption scheme will give away the length of the message, but not the content of the message. But he also gets the same auxiliary information, and his task is also to come up with this target here. So that's kind of the setup, and here is the actual definition of semantic security. So there's a bunch of quantifiers here. So what you're going to ask is that for every adversary, and actually for every efficient adversary, but just let me skip that for now. So for every adversary in the real world, there should be a simulator. So there should be a simulator in the ideal world, such that for any ways, so I'm reading out this thing here, for any ways to come up with a message, and for any ways to derive auxiliary information about this message, and a target function of this message, the chance that they succeed, these two guys, should be roughly the same. So the probability that the adversary A on input the encryption of M and this auxiliary information that he comes up with a target, that should be very much related to the probability that the simulator only running on the length of the message and this auxiliary information that he can come up with this target. So maybe quick raise of hands, who has never seen this before? And who has seen it before? Okay. So it's about half-half. So this takes a while to actually digest somehow. Why? To kind of appreciate that this is the notion of security that you actually want from an encryption scheme. So what does it intuitively mean? And I mean, I can go over it once more, but maybe you should just stare at it for a while if you have the time. But so intuitively, it's like whatever your adversary is able to do, you should be able to explain that in a way that is not using the encryption of M. So that's kind of what this says. So that basically means that there isn't any information about M left once you encrypt it. So once you kind of see that this is actually the notion of security we want, it turns out that it's very inconvenient to work with this thing. So classical cryptographers have also realized that. And what they came up instead is this notion of indistinguishability. So this is defined in terms of a game. It's called this private key eavesdropper game. It's a game between the adversary and the challenger. It's pretty simple. It works like that. So the adversary sends a message to the challenger. The challenger, he flips a random coin, a random bit, and depending on the outcome of this bit, he either encrypts this message, call this C if the bit is 1, or he encrypts the 0 message of the appropriate length, of the same length as the message M, if the bit is 0. And he sends this ciphertext over to the adversary, and the adversary has to decide which of the two he did. He sends back a bit B prime, and he wins the game, the adversary, if this bit B prime equals this bit here. So basically he has to decide whether the 0 message has been encrypted or this actual message that he sent. And here's the definition of indistinguishability. So an encryption scheme is called indistinguishable if for every efficient adversary A, the chance to win this game is upper bounded by 1/2 plus something negligible in N. So notice, it's very easy to win this game with probability 1/2. You just pick a random bit, and with probability 1/2 you're right. But the point is that if it's a good encryption scheme, then the ciphertext really shouldn't tell you much about M. So you should really not have a clue in which case you are. And if that is the case, then we call the scheme secure. Now, the nice theorem that one can prove is that these two notions of indistinguishability and semantic security that I showed you on the other slide, they are actually equivalent. So this has been shown by Goldwasser and Mikali in '84, that these two things are actually the same thing. So somewhat confusingly, that also sometimes people call this semantic security instead. But in fact, what they mean is the other thing, and this is just the thing that is way easier to work with. So far, yeah, 4 minutes. This has all been classical. So let me come to what we actually did. So what we did, we basically translate this to the quantum setting. So we give a formal definition of quantum semantic security, and we show in that case as well that it's equivalent to an according indistinguishability notion in a quantum setting. So let me explain you that, and then we'll see how far we get. So here's our notion of quantum semantic security. Now everything is quantum, so in a sense you want to encrypt quantum states. So here's your message generator, and now it produces 3 registers, possibly entangled. The first one is kind of the message, the second is some auxiliary information, and the third one is the target. And what you do is very similar to before. You take the message, now this quantum state, you encrypt it, and together with the auxiliary information, you give it to the adversary, and the adversary is now asked to come up with a state that somehow cannot be distinguished from the target state. Notice before we were really checking equality. Here actually kind of less restrictive, somehow we're checking equality of 2 quantum states. That's a bit hairy, but so what we do is we just give it to a distinguisher who does whatever he wants. He just outputs a classical bit, either 0 or 1. And we want to compare this real world to the ideal world, where we similarly just give the auxiliary information to the simulator, and the simulator is feeding that to the distinguisher as well, who also gets this target register. And the definition, our definition is now that, again, for every adversary in the real world, there is a simulator in the ideal world, such that for any ways to come up with these messages, and for any possible distinguisher we put here, these 2 probabilities to output 0, 1 are basically very similar to each other in these 2 worlds. So that's our translation of the classical notion to the quantum world. Now once you see it, you think, oh yeah, obviously, but it turns out there's many little details you can change here, and that give you different notions, so it's quite tricky to actually come up with the right one. And why we think we do have found the right one is because we can also show equivalence to kind of the quantum version of indistinguishability. So this one is easier. Just the same thing as before. Let's have the adversary send a quantum state to the challenger. The challenger still makes a classical coin flip, and either encrypts the all 0 state of the same length as row m, or he actually encrypts this message and sends that ciphertext back. Now these are all quantum transmissions, and the adversary has to guess which one of the two cases happened. So he wins again if B prime equals B. And so the according definition would be if a quantum encryption scheme is secure, according to this indistinguishability notion, if for every adversary the chance to win this game is at most 1/2 plus negligible. And again, we are able to show this theorem, namely that these two notions are equivalent. So an encryption scheme that is quantum semantically secure is if and only if its quantum indistinguishability is secure. All right, so now, yeah, let me do this and then I will skip the rest. So I had this level, this kind of threat levels. So what one can do is like one can look at more powerful adversaries, those who are, for instance, able to kind of query encryption oracles. So here I kind of upgrade this game now to so-called chosen plaintext attacks by giving the adversary the possibility to ask encryptions from the challenger. So like whenever during this game, before the final step, the adversary can ask some quantum states to be encrypted. And you can do this many times. You can even do it adaptively. You can do it before this challenge phase and after. And we call an encryption scheme secure if the probability to win that game is still upper bound 1/2 plus negligible. Now notice, and what we are able to do is again kind of upgrade the semantic security version to a CPA version as well, and they remain equivalent. But one thing to notice here is that this type of security now requires you to have what we call randomized encryption. So imagine if the encryption, so you can think of this also in totally classical terms. Imagine if the encryption is deterministic, so you always get the same encryption if you ask for the same on the same message. Well, then this game is easy to win, no? Because you just send a message here that is not zero, and then you also ask for the encryption of it, and you simply compare that to what you get back here. Well, so if it's not randomized encryption scheme, then you will win this game easily. So if you want to fulfill this kind of notion, then you will need some more advanced form of encryption, and this so-called randomized encryption. You could take this even one step further and not only allow the adversary to ask encryption queries, but as I said, maybe you can also allow him for asking decryption queries, and then you get a notion that is called chosen ciphertext attacks, so CCA1, there's a CCA2. So again, we can show equivalence to quantum semantic security, and they're like strictly, they imply each other. So this is a strictly stronger notion than the CPA, and it's also strictly stronger than the regular one. So like if you give the adversary more power, well, it makes it more difficult to find an encryption scheme that is secure according to this notion. So do I have any time left or not? Okay. Well, then I will just simply skip the rest because. So that was kind of the definitional part of our paper. Then we also have two constructions. One of them, this one was actually used in Bill's talk when he was talking about CCA1, secure encryption schemes. We have one construction for a secret key encryption scheme, and we have one construction for a public key encryption scheme that encrypt quantum data. But so as I don't have time, I will just simply skip that and come to the conclusions. So the conclusions are basically similar to that. I've already said it. Obvious open question for the experts, because I didn't have time to explain, is like how would you define actually quantum CCA2 security? So that just quickly in words, it means that you give access to the decryption oracle after the challenge phase, because then you shouldn't allow the attacker to actually ask what was the challenge, but you somehow have to cleverly define that case. And I will leave it at that, and thank you for your attention.
Thanks, Christian. Any questions? Anyone want to see the public key? All right, so before we thank Christian and all the speakers of the session, Christian is going to make afterwards some announcements, so don't leave. But before that, let's thank Christian and all the speakers of the session.
Yes, now so I quickly changed my hat from a contributor, talk, presenter to steering committee member and actually chair of the steering committee of next year's QCrypt. So I have two quick announcements to make. So first of all, we're looking for proposals to host QCrypt 2018. We will handle this process in a two-step process. The first one is pretty easy, and the deadline is like in 1 month from now. So if you intend to, if you have a plan to host QCrypt 2018, please send us a letter stating basically these few things: the name, affiliation of the main organizer, possible conference dates, the location and the size of an intended venue. And as you all know, we try to rotate in terms of continents. So right now we're in North America, next year it's going to be in Europe. So ideally proposals from outside these two continents, which basically gives like Africa, Asia, Australia, and South America. So those bits will be preferred. So just send us a simple letter of intent to this email address until Friday, 14th of October. We will sift through those, and then we will ask the top contenders to work out a full proposal. You will also find all this information on the website and in the email that we will send to you shortly. And there as well, you're going to find a survey which we kindly asked you to fill out because it's very useful to get feedback from you guys. So there's a link either already now available or soon available. It is available, I just see, on the QCrypt webpage under announcements. And so please go and fill in this survey. It really helps us looking forward and adapting things to your needs. And then last but not least, in the name of the whole steering committee, I'd like to thank our general chair and also chair of the steering committee very much. Yikai, please come to the stage for putting together a great conference. And we got you a little something. Maybe you could. Thank you very much for all your efforts. I know that's been a lot of work, but I think everything worked out very well. And so, thank you very much for a great conference, Yikai.